Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best-tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high-quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius podcast
with Richard Jacobs.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. I have Bruce R. Sutherland. He's the Associate Editor of Physical Review Fluids. He's part of the Department of Physics and Earth and Atmospheric Sciences at University of Alberta. And we're going to talk about modeling of environmental and industrial fluid flows and microplastics and fluid dynamic type issues. So Bruce, thank you for coming.
It's nice to be here. Thanks, Richard.
If you would, tell me a bit about your background first, and then we'll talk about what you're working on today.
Sure. So I was originally trained as a mathematician, but then I switched to physics for a PhD, and then I went to Cambridge where I started doing lab experiments in physics and math department combined. Then I was hired here in mathematics, but then I now switched over to physics. The reason I give all that story is I study fluid dynamics, and it really lies in between mathematics and physics. So hence I got this sort of weird mixed background.
Okay. But what are you working on right now? Are you modeling microplastic movements, or are you modeling more just the large scale movements of fluids and air and oceans on Earth, or what's your current research?
Yeah, in terms of right now, there's a sort of a bunch of different things going on at the same time. Some of it is just looking at the propagation of waves inside the ocean. That's a bit unusual. People think of waves on top of the ocean, but actually there were also waves that move inside the ocean called internal waves. In fact, the same waves move inside the atmosphere, and sometimes you can see that when you look at cloud patterns that are banded and they look wavy. That's actually you're looking at a wave. I don't know how much you want to go down this rabbit hole, but they move inside the ocean because the density of the ocean gets larger as you go to greater depth. It's warmer at the surface because the sun is shining there. It's colder at depth. And so the waves can move up and down due to buoyancy. So a lot of people are interested in, oceanographers are very interested in these waves because they're the primary way through which the ocean mixes. And people want to understand ocean mixing because that's an important part of understanding the Earth's climate. It's a way that you can take heat into the ocean at the surface and through mixing, carrying it down to depth. So we're looking at fundamental problems and how those waves are generated, how they evolve, and how ultimately they break due to mixing. So that's part of the work. Some of the work is looking at how waves are created by turbulence, thinking of, say, the top of a thunderstorm hitting the stratosphere and the atmosphere. That can launch these waves. That hasn't been studied too much, so we're trying to get our head around that. But really the work that's consumed me most recently is studying aspects of microplastic research. My particular niche here is to look at thinking of plastics in a muddy river. So you have a river like the Mississippi with suspended clay, and asking how does that plastic interact with the clay? Can it interact with it in a way that can make the plastic settle more rapidly? For example, when the river reaches the ocean and suddenly descends to depth. So we're really trying to understand, is a lot of the plastic put into rivers, is it actually being deposited near the coast? Or is a lot of it still getting out to the middle of the ocean? We really don't understand anything about where the plastics are going right now. So I'm looking at that little bit of the piece.
Does this at all tie into like do you get any information from the large gyres, the Pacific Garbage Patch and these huge, maybe observable from space, I don't know, formations of garbage? Does that tell you anything about modeling microplastics, even though it's on a different scale?
Yeah, so it is important that it's a different scale. So the floating plastic, like the bags and bottles that are in this infamous Great Garbage Patch, which lies between Hawaii and the western seaboard of the States, those plastics, people have seen them being ingested by whales and they affect seabirds and so on. But the plastics we think that are the most insidious are so-called microplastics. These are plastics that are less than 5 millimeters in size, and they can go down to the size of dust. You couldn't even see it with your naked eye. And the way those move and even how they're created is very different from the relatively easy problem of just looking at plastic bottles floating on the surface of the ocean, because they're carried around by waves and winds and gyre circulations, but they're not being broken up by turbulence. They're not being carried down to depth and ultimately settling where they might be ingested by microorganisms that then carry the plastics back up the food chain to us.
I haven't run it. I've interviewed probably about 15 different microplastics researchers, and no one seems to be taking the time to model. I'm imagining like this little wave tank with some plastic bottles in it and an ultraviolet light on it, and they're sloshing back and forth, and there's sand and all that, and trying to model the breakdown, how fast it happens and what it looks like. Do you have any idea, if anyone's modeling, again, how long it takes different plastics to break down to different regime sizes, microplastic level?
Yeah, it's a really good question. There are so many unknowns involving microplastics, and one of the big ones is how are they even created? Some of them are released into rivers and the ocean as microplastics. For example, a lot of microplastics used to be in toothpaste. Even plastic fibers from your clothing get into rivers. But also, we know that a lot of plastics go in as large plastics that you can see, whether it's bags or bottles or maybe plastic fishing nets, and somehow they're broken up. And there's two ways it happens. One is through turbulence. So just the turbulence in the ocean maybe breaking waves that can bend and twist the plastic and make it snap. And so as for your question, who's looking at this, to my mind, there's about 3 labs in the world right now that are focused on that. That could be an underestimate, but I know certainly of 3. And they have these boxes, they fill with water, and they put in these long fibers, and then they have these stirrers at the corners of the box to make the whole thing turbulent. And then they have 3 cameras pointed at the tank so that they can identify exactly where the fiber is in 3-dimensional space and look at it bending and seeing if it breaks. So that's research that, to my mind, started maybe 5 years ago, and it's still, I'll say, at the idealized state where they're trying to make sort of uniform turbulence, if that makes sense, as opposed to the realistic ocean scenario of saying a white capping breaking wave, which is much messier than the idealized turbulence they're looking at. But
you'll still get much closer than knowing nothing. And just saying,
absolutely.
It takes a long time. How long is long? Who knows?
Yeah. And I'll say the other part with plastics is that it is known, depends on the plastic, but plastics do get more brittle over time with exposure to sunlight. Although it depends on the plastic, some estimates say that plastics can hang around without degrading due to sunlight for decades even, whereas others, like plastic bags, get more brittle on a faster rate. So even the property of the plastic changes in time, and that makes the problem even more complicated, because normally when we look at something idealized, we like to think we know exactly the properties of this solid that we're bending and twisting, but this is something that's actually changing its structure, and even how it changes its structure in time isn't that well understood. That's more of a chemistry problem at this stage.
One thing I will say, I think I've realized is a bunch of people have mentioned that, from doing laundry and from clothing, there's a high percentage of fibers that constitute microplastics, but those really aren't degrading in the environment. They're coming ready-made and ready to go. As soon as I do my laundry and wash it and dry it, out it goes into the water supply, and it can end up in, a lake or stream or ocean if something happens. But I would guess there wouldn't really be any degradation. It would just be the fibers are created at that one point at the time of the washing, and out they go, ready to go and pollute and be microplastics right off the bat. They don't need to degrade.
Yeah, and that's another really good point. It's not just fibers in your clothing, but there's a very good reason why we have plastic milk containers and plastic bottles for shampoo and so on. Plastic is really inert, so it doesn't react with food and it doesn't react with things. So you might think, well, what's the big deal? So let's say I ingest 5 grams of plastic a week, which is a recent estimate in a paper I read. Is that a big deal? Well, for my thinking on this is it's not so much the plastic that might be concerned, but plastics provide a site where toxins can grow and develop on the plastic, whether it's toxic biology or just toxins in the ocean water or lake water that attracts itself to the plastic and sticks to it. And then for big humans like us, maybe that wouldn't matter, but these plastics, when they finally settle, are being taken up by small benthic organisms, mussels, clams, and even smaller creatures. And there are studies that show by ingesting these plastics, it affects their reproductive system. And again, these are all still very early studies, so the degree to which it affects it and how much it depends on the type of plastic and maybe what toxins were attracted to it, that's really not well understood right now. But if there is a possibility that these plastics become an efficient way for microorganisms to ingest toxins, hence damaging that part of the ecosystem, that then filters up through the entire ecosystem. So with microplastic research, it's not like there's a smoking gun, but because we don't know so much about it, including whether or not it's an active danger or a potential danger, we're just being active now in trying to research it and understand as much as possible so that if indeed aspects of it are very dangerous, at least we'll have already hit the ground running in the research.
So currently, what are you modeling and having some success in understanding? Is it how the, plastics move in bulk and become microplastics, or is it microplastics themselves moving in, the oceans, or like what are you modeling right now?
work on microplastics, again, it's a niche, is through laboratory experiments. And they're dead simple experiments. I just have a beaker, I put in some clay, been using bentonite recently, and there's kaolinite clay, there's different types of clay, and I mix in some measured mass of microplastics, and I put in different plastics and which have different buoyancies and different sizes, so I can control the size. And then I just look at, after the clay settles, how much plastic is still floating on the surface. And when we did these experiments last summer, we were shocked. I'm still shocked that even with a relatively small amount of clay, like 1 part to 100, 1 part mass of clay to 100 parts mass of plastic, the clay gloms onto the plastic. There's some kind of an attractive force. It's not just sitting side by side, but the clay attracts to it and carries it to depth. So again, with say 1 gram of clay and 100 grams of plastics, we found that about 80% of the plastics were carried to depth, even though the plastics were buoyant in water and they should have all been floating. So that's a concern, because it says clay typically can stay nicely suspended in rivers when it's fresh water. But when clay comes into contact with seawater, clay itself, in the jargon, it flocculates. The clay attracts to itself and grows into larger and larger clay particles, and that's why they rain out so quickly near the coast. And so if they're also being attracted to plastics, it means the plastics are actually settling near the coast. And of course, that's where all the sensitive biology is. You know, all these microorganisms.
Is there a way does the clay naturally like flocculate? So it sounds like, I guess there's a suspension of clay that, I guess at first it sequesters the microplastics, which may be a good thing. And it's sitting, in the bottom of rivers, and eventually it gets sloughed off and then goes into brackish water and then kind of stays in the water column there. Like, would you mind explaining a little bit more?
Yeah, of course. Yeah, when I'm talking about clay, I'm not thinking of this clay sediment at the bottom of a river. I'm thinking of muddy rivers like the Mississippi, the Amazon. Like pretty well every major river does not look blue; it looks brown, and that's because it's a suspension of fine particles of clay, which, as you were saying, ultimately come from either being washed into the river to begin with by water running over land, or just through some turbulence in the river picking up some clay from the ground, from the bottom of the riverbed. But all these rivers, big rivers, if you look at them, are all brownish, and that's because they're suspensions of tiny particles of clay. Clay, for what it's worth, like the size of clay, it's a micron. That doesn't help much, but it's about 100th the width of a human hair. So it's super tiny, and we were finding that even with plastics that were the width of a human hair, these tiny clay particles were able to glom onto it and carry it to depth, even though that plastic particle was buoyant. And so we're thinking that the muddy river and the plastics are all living together, but the clay comes into contact with the ocean, and that's what makes them flocculate, and that's what makes them fall to depth. But they've already glommed on to some plastics, so they're taking those plastics down with them.
Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
So this could be a good thing. I mean, if fish feed into the mud, that's no good. But, I mean, again, if the mud sequesters a significant number of plastics, That may be a very good thing. Maybe you could do, I don't know, limited dredging in an area. I don't know.
Now, to be honest, that's a good
And
point.
replacement. You know?
If we knew where the plastics were, that would be a good thing, because then, yeah, we could dredge or something, or at least we could target our monitoring of the ecosystems, the marine ecosystems, in those places where we know they might be exposed more to plastic. So right now, this is all seeing if we can understand it. A quick little fact, by the way, when it comes to plastics going into the ocean, it's estimated roughly about 20 million tons of plastics are dumped into the ocean every year. But when people survey and look for plastics, say at this great garbage patch and so on, they have only observed 300,000. So they've only observed about 3% or less of the plastic that's produced in any 1 year. So really, we've only observed much less than 1% of all the plastic that's been produced over the last several decades. And so that's the question that we don't know. Where is the missing plastic? And so my research is looking at this one part that says, well, maybe some of it is down at the coast, but that isn't going to be all of it. There's a lot of the plastic that's put in the ocean comes from just plastic fishing nets and even just debris, garbage thrown overboard by fishermen.
What would be interesting in rivers is, you know where it's coming from, you know where it's going. It's a flow-through system. It's not a closed system. But what if you had a program of seeding certain rivers at an early point in the river and then harvesting or dredging down below where, let's say there's backwaters or eddies where this clay silt that you put in to seed the river, to suck out microplastics from it, it always collects downriver in this one spot, for instance. So you do like a seeding and dredging, and maybe in that way you're able to reduce the material that goes into the ocean if the river empties into the ocean and keep the river cleaner.
This is another thing, of course, that would cost money and a whole bunch of other things. And this is the other side of this coin where people still don't know how dangerous it is. And so I find it hard to imagine that governments, industries, whatever, would invest a lot of money to do extensive dredging until they knew this was actually a bona fide problem. But as for observations, I have a colleague in sedimentary geology who studies estuaries, and he says every time he digs up a sample of mud from the bottom of a river that's about to enter the ocean in an estuary, it's always got microplastics in it. So it is clear that, yes, the plastics are settling there, but it's still a question of, well, what fraction of all the plastics that were in the river settled right there? Was that just 1% of the plastics? Or maybe it was, hopefully 80, 90%. But until we know whether it's a tiny fraction or a huge fraction, it could be that dredging, sure, you get your 1%, but you're not actually dealing with the big issue where the majority of the plastics go. So again, it's just
maybe you can use a river again for an outdoor natural lab. You don't have to dredge tons of material, but maybe you get a 3 foot by 3 foot square part, where stuff tends to settle, and you as part of your, whoever is part of their experiment goes and removes, let's say, a couple inches from that area. Then they seed upriver and they watch and see that area. They take samples over time and they see what comes down and how long it takes to accumulate and all that. I mean, it could be like an outdoor lab that could experiment in that way, at least to see.
Yeah, I follow you. Again, that's not something that would be in my research, but there are people who, I think there would be lots of regulations and laws against people just dumping and seeding plastic and seeing where it goes. But there
it wouldn't be seeding plastic. You'd put in, let's say, like virgin clay or the type of material that agglomerates this stuff, because it would have a very high affinity for any plastics that are in there as it floats down. So you'd put virgin material in there. You watch to see what the resultant concentrate is of the material, the clay microplastic mix at your designated site downstream. I just wonder if that would be useful to figure stuff out.
Yeah, if you could somehow tag the clay so you knew the virgin material you put in when you observe it further downstream, it's the same material. Again, clay comes in so many different varieties, shapes and sizes and so on. The only thing I could think to tag the clay would be to make it radioactive, but I think that's a bad idea.
Yeah, that's true.
I was going to mention there was an accident that happened about a year and a half ago. There was a big container ship carrying what are called nurdles, which are about, I'll say, about a 1/4 inch diameter balls of plastic. They're the raw ingredient that are used by industry to then construct plastic bottles or what have you. And so this huge container vessel contained like gazillions of these tiny little plastic beads, but then it went on fire and it tipped, and all the plastic nurdles were spilt into the ocean off the coast of Sri Lanka. And that was fantastic. Well, it was terrible, but it was great along the lines of what you're saying, because now you had at this fixed location a sudden dumping of a certain type of plastic put in near the coast of Sri Lanka, and then people could go along the coast and measure where did the plastic wash up, when did it wash up, and so on. So that one accident actually gave us a lot of insight into how plastics are transported when they're dumped in the ocean but near the coast. With the good news being that it seems that most of the plastic released near a coast actually remain near a coast.
I guess there's a long pathway. So like first, like you said, you got to demonstrate that these plastics are harmful and how. And then I could see if, regulation would classify microplastics as a waste stream, let's say for businesses, at least for a start, and then it could set limits on, the percentage or morphology or whatever of the plastics they quote unquote emit in their waste streams. They could do some remediation, but it sounds like there's this whole pathway that has to be laid down in order for this to happen.
Yeah, the one progress that has been made regarding government stepping in to reduce plastic pollution, going maybe 7-8 years ago, a lot of countries banned the use of microplastics in things like toothpaste and abrasives and makeup and hair gel. Microplastics were in tons of consumer products, and that got banned. So at least now we don't have that source of plastics. And now countries are beginning to ban the use of plastic bags. It's taking a while, but they're staging, some countries are staging in the elimination of just consumer plastic bags like you would get at a grocery store. And so that's also making some progress there. But when you look at all the plastic we use, again, in terms of milk jugs and wrapping, saran wrap on everything you can find in a grocery store, we're certainly a long way away of eliminating the source of the plastics.
Does anyone, again, have any idea if I take a plastic milk jug, throw it away, and in a water source and it degrades, how many microplastics it creates? Like, to what extent does it break down? Does the whole thing eventually turn into tiny pieces, or does monolithically a hole blow open in it and around the periphery, like some of it will turn to microplastics, but you still retain, let's say 90% of the whole plastic bottle that remains macro, but a small fraction becomes micro, but that's a ton.
So that has not been studied. Again, the people I know who are looking at the interactions of plastics with turbulence are working with plastic fibers, and some of that is just an issue of scale. If you wanted to look at how a milk jug breaks down, it's hard to imagine having a lab big enough that would have realistic waves and turbulence, and the breakdown might take place over the course of weeks, but maybe months, maybe years. So you'd have to have this thing running continuously and monitoring. So it's just not feasible as far as lab experiments. But getting back to what you were saying, well, maybe you could just tag a jug, release it into a controlled ocean environment, and then just come back and check on it, or have maybe a little GoPro camera attached to it that hopefully won't die in the salt water. Maybe in situ get some measurements, but right now that it really isn't certain about the time scale of how these things break down.
So what's your goal with your research? What are you trying to, what piece of the puzzle are you trying to fill in here?
Things always evolve. You get results, and then it inspires you to study something completely new you hadn't thought of. So right now, again, my focus is looking at the interaction between clay and plastics. And I still don't understand why the clay sticks to the plastic. I've been working with my geology colleagues, and we've tried a whole bunch of different things under electron microscopes and various chemicals and putting in biology, and we still don't have a clear understanding of why this happens. So I'm focused on that problem right now, and what I would like to do eventually, I've just been looking at nice quiescent water, clay, plastic in a beaker, and let it settle, which takes about overnight to happen. But the real problem would be a moving, turbulent river. But that is something that I can make on a lab scale because I'm dealing with tiny particles, tiny clay, and I can get a, say, a meter cube box and make it turbulent, maybe even make some surface waves, and then look at how that influences the rate at which the clay and the plastic is settling. So that's I'll say, a goal that may go over the next 5 years.
I guess maybe some of the major factors would be, pH of the water that this is going into, salinity, and then the charge of the clay and the charge of the microplastics. Is it opposite? Is it same? I mean, maybe these would be some major factors that would govern what happens.
Yeah, so I originally thought it was because the plastic was charged. Like anyone who's got styrofoam beads in packing knows that you have static electricity like crazy. So I thought the plastic must be charged, but we measured if there was any charge on the plastic, and there's none. So it's not charged at all. So it's not an electrical attraction. Then we thought, well, maybe biology, because microbes love to grow on plastics. So maybe biology was growing on the plastics, and that made a sort of a sticky substance from what they secrete, and the clay gloms onto the sticky substance. But so far, no luck with that either. So it's a bit of a mystery, but it's incontrovertible that the plastics settle, and that I've seen the particles under electron microscope, and it is just coated with the clay. It's not just sort of side by side, but the clay is definitely stuck to the plastic, though for reasons I don't understand just yet.
And I guess also, too, in various bodies of water with, again, based on salinity, et cetera, what is the size at which a plastic or clay will precipitate versus stay suspended, in all kinds of different conditions? Maybe that gives some kind of hint, too.
Yeah, so that's more the short-term goal of the research. I'm just trying to understand the phenomenology right now. But really what I would like to do, still working with this beaker clay plastic setup, is look at a wider range of plastics, a wider range of sizes of the plastics, from maybe even centimeter scale going down to this micron, tinier than a human hair scale. And so really try to categorize, if you have this type of plastic and it's this size in this kind of clay concentration, you should expect so much, this amount to sink. So that's the shorter term goal, after which the plan would be put in realistic things like turbulence and so on.
Well, when you look under a microscope, is the clay and plastic bonded? Is the clay, surrounding the plastic somehow and coating it? Like, what does it look like?
Yeah, so clay, if you look at it under an electron microscope, it's actually, it's plate shaped. It's not a sphere, but they're actually shaped like little plates. What you see when you look at the plastic and the clay together is the plates are flat, flush against the surface of the plastic. So they're not just sort of tumbling around like you randomly threw some cards in the air. They're really pasted onto the surface of the plastic, which is why we know they're stuck there. They're not just sort of tumbling around.
Does the plastic somehow organize the clay? Like, do the plates line up in any pattern, or does it still look chaotic?
Yeah, and again, so that we don't know. So I don't do the experiment looking under a microscope while it's running. I just look at the final end product after everything's settled. And I'm not sure how, because it's so small, you really, even with a standard microscope, I don't think you could look and see the process happening as the clay was attaching to the plastic and settling.
Is there a critical size below which the clay will adhere? Like, what if you had a macroscopic, 2 centimeter by 2 centimeter piece of plastic that's the same, molecular formulation as the microplastics, and what if clay sticks to it? I mean, is there a certain size threshold that this happens or doesn't happen?
Don't know, but again, that is the short-term goal, to get up to studying that, hopefully in the next 2-3 years.
Okay. Well, very good. What's the best way for people to find out more about your work? Where can they go?
Maybe not just my work, but we ran a workshop back in February. We had a lot of excellent speakers, and we also wrote a summary proposal that was written for the non-expert. So people, if they go to that site, will get a really broad idea of all the different issues of what we know and what we don't know, especially with that report. So the site, if you Google searched it, the workshop was at the Banff International Research Station. The acronym is BIRS, B-I-R-S. I had to give all that information so you don't think I'm saying BIRS, B-E-E-R-S, it's B-I-R-S. So if you Google search BIRS and microplastics, it will send you straight to that website. And then you can read our executive summary and see some of the videos and get more of a visual background of what's going on.
Okay, very good. Well, thanks so much for coming on the podcast. I really appreciate it.
Yeah, thanks for your excellent questions, Richard. I enjoyed myself. Thanks.
Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with the ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best-tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high-quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.